gives me confidence. We're good to go?
Yep, you're good.
Okay. So how's everyone doing today? My name is Daniel Roberts, and today we're going to be talking about quantum computing. So who here has heard of Gordon Moore? A couple of people. That's good. He is the co-founder of Intel, perhaps one of the largest chip manufacturers in the world. And when he first started the company, he made a prediction. That prediction was that every year the power of a CPU would double. And it held true for so long that they eventually made it a law, and it became known as Moore's Law, which we see here as a picture, and essentially the graph goes up with the power and the date, etc. But there's a problem with this graph, and that's that recently he had to revise his law because every 18 months the power of CPUs now increase. So what does this tell us? It essentially tells us that the rate at which we can increase power of a computer is slowing down. And part of the reason for that is the transistor. Now the transistor is what gives a CPU its power. It's what enables it to read and write in binary. So how does a transistor work? Essentially, you have a source over here, you have a drain, and then you have a gate. Now when a positive voltage is applied to the gate, electrons can flow from the source to the drain, and when that voltage is taken away, the electrons are no longer able to flow between these 2 points. So essentially that gives you your 0 and 1 in binary. And the reason it's slowing down, Moore's Law, is because you can only make a transistor so small. Today's transistors, we now have about 2 billion transistors on the average CPU. So what do we do after Moore's Law? What do we do after the digital age? My argument would be that quantum computing could potentially still increase speed, even after the digital age has passed. So what are we going to talk about today? Well, first, I'm going to teach you guys some basics of quantum mechanics. You have to understand, how this stuff works if you can attempt to program on it and use it in the field. So then I'm going to talk about how those mechanics can be used in quantum computation, how we can actually compute things using these mechanics. And then, being the Society of Software Engineers, we're going to talk about the software and how you can actually program one of these machines. And then we're going to go into some current technology and what currently exists in the world. And I think you'll be a little surprised at what currently actually exists. Also, if you do have any questions at any point, please don't hesitate to ask. This is a very complex topic. It can get very confusing very quickly. So what are quantum mechanics? Quantum mechanics are essentially the birthchild of Albert Einstein. In 1905, he wrote a paper that essentially outlined the basics of quantum mechanics, and he theorized that they basically existed. And it's interesting because quantum mechanics basically refer to the mechanics of particles on a subatomic level. So while classical mechanics refers to things like objects such as you and I, and the fact that we hit a wall and we can't go through the wall, quantum mechanics refers to if an electron was fired at that wall, it can go straight through it through a process called quantum tunneling, which I'm not going to get into that whatsoever. But essentially, the way atoms work is completely different from how classical mechanics work. So that's why it's so powerful, and as you're going to see in a few minutes here. But it's also why there's a lot of problems with quantum mechanics and quantum computation. So one of the most basic principles of quantum mechanics, also probably one of the most confusing, is quantum superposition. There's essentially 2 parts to quantum superposition. The first part I'm going to describe right here. So if we have this loop and the electrons are flowing that direction, the little red ball over there is an electron, and this is the exit of the tube. Which direction do you think that electron is going to go around that loop to get to the exit? You'd think it would be a 50-50 chance, right? You'd think that it would be a 50% chance it can go this way or a 50% chance it can go that way. But in reality, what ends up happening is the electron goes both ways at the same time. I'll just give you a moment to absorb that. It sounds crazy, right? And one of the things I want to emphasize with this, as well as trying to understand superposition, is that there's nothing in our physical world that can model quantum mechanics. And this is the reason a lot of people struggle with it, is because, if you went up to that tube, you'd have to make a decision of which way you go. You can't go both ways. But an electron can go both ways at the same time. Essentially what this means is that an electron can be in multiple states at the same time. This is just a model, but electrons do actually flow through both veins at once. but this is more of a model to model the fact that electrons and particles in general can be in multiple states at the same time. So the way that this was proved and the way this was found was through something known as the double slit experiment. In the early 1900s, Einstein observed this, along with many other physicists, that the problem was you had a bunch of electrons over here, in this case they're photons, particles of light, and you were shooting them through two slits in a wall, like this. And what you would expect to see is you would expect to see two patterns here, where all the electrons were hitting. But on what actually happened was you get this pattern on the back wall like that. And this is called an interference pattern. Essentially, the particles are going through, and they're going at different angles, and some of them are canceling each other out, which is why you don't just have the entire wall covered in electrons, but you end up getting these lines and strips. And this actually confused physicists for a very, very long time. Einstein couldn't wrap his head around why this was actually occurring until a man named Erwin Schrödinger came along. Now, you've probably heard of Schrodinger's equation, the Schrödinger cat paradigm. Erwin Schrödinger was a physicist by nature, but he came along and he applied some mathematics to this model. And what he ended up creating was the Schrödinger equation. And what the Schrödinger equation essentially states is that it's a probability distribution of where the electron will be at a given time. So while superposition states that electrons can travel in two different ways at the same time, and they can exist in two states at the same time, what superposition does, or what, Schrodinger's equation gives us, is it allows us to predict where that electron will be at a given time. So essentially, in the first example we looked at, it'll either be in the upper arc or the lower arc. And Schrodinger's equation allows us to mathematically calculate the probability that it will be one over the other. Now, a scientist by the name of Niels Bohr then came along, and he looked at Schrödinger and he said, there's got to be more to this. This can't be, the only thing going on. So what Niels Bohr ended up basically stating was that the act of measuring the particle is what causes the probability of the particle to be there. Einstein was very, very confused by this for obvious reasons, and he couldn't understand why this was happening. And his famous quote here, God does not throw dice. He couldn't understand that our world essentially relies on probability and runs on the fact that it's a probabilistic equation. So Bohr came along and he then said, okay, so the act of measuring a particle is what causes its state. And Einstein was like, no. The particle was always in that state. We just happened to measure it at that point and found it was in that state. So this can get very confusing, as I'm sure many of you are a little confused right now, but hopefully it's going to make more sense towards the end. So quantum spin. Quantum spin actually is I don't know why they named it spin. Well, I do know why they named it spin, but it should not have been named spin because it gives you the impression that the particle is actually spinning on its axis, which it's not doing. Quantum spin, for all purposes for this presentation, the only thing you really need to know about quantum spin is a particle can either exist in a spin up position or a spin down position. And that's essentially our two states right there, spin up and spin down. The only little caveat is that because of superposition, it can also exist in a state between those two states. So you could have 60% chance that it would be up and maybe a 30% chance it would be down, and then a 10% chance that it could be elsewhere. You have no idea until you actually measure this thing. But the only thing you really need to know about spin for now is that it's up or down. Spin up, spin down. So quantum entanglement, this is probably the most controversial and most misunderstood aspect of quantum mechanics. It's very, very confusing, and most people look at it and go, okay, that's just not possible. That is not possible in what we believe exists in the universe. So what quantum entanglement is, essentially, is if you have two particles, you bring them together, you match up their states and their spins, and then you take those particles apart, and what actually happens is they now are connected through some weird method that physicists still don't understand. And you could take this particle millions of miles away, and it will still be connected. What this essentially means in terms of quantum spin and other things is that if you measure one particle over here and it's spin up, the particle over here will be spin down. They become dependent on each other. So they are essentially communicating through an invisible wavelength or something over millions of miles. And this also is instantaneous too. So it breaks the law of relativity because it travels faster than the speed of light, which people looked at this and they were like, okay, that's ridiculous. That doesn't happen, right? And Einstein, until his death, refused to believe that this was actually happening. Until it was proven in 1970 by a man named John Clauser, who he's a pretty important figure in quantum mechanics because he essentially proved through very, very clever mathematics that this is actually what's going on, and entanglement is actually real, and we can measure this, and we can use it. One of the many uses for entanglement is quantum teleportation. Now, this sounds like a fantasy. It sounds like something you'd see in Star Trek. It sounds like science fiction. But we can actually do this. We can teleport particles from one location to another using quantum entanglement. So how do you do that? So essentially, you have a particle to start with. Then you bring in a second particle. We have a white and a black particle. You entangle their states so that now they're gray. Now they share each other's properties. And until we measure one of these, we don't actually know what the state of this thing is. But they've now become dependent on each other. You then bring in a third particle, a blue particle, and try to entangle that with the first one. And what essentially happens is you then go to measure the other one at the other end, and what happens is that blue particle has now been teleported essentially to this particle over here, and the original has been destroyed. So this is kind of a concept that people struggle with, and they also argue if it is really teleportation or not, because you're essentially destroying the original to recreate the new one. So if you were looking at this in terms of humans, for example, it's been theorized that you could use this to actually teleport humans. And I want to take this time as well to point out that this is real. This isn't something that's theory. This has been proven. This has been done many times, that you can actually teleport particles. The only little caveat with this is that the teleportation is essentially, it's not random itself, but the state in which the particle is random. So you can't predict even using Schrodinger's equation, you can't predict what state this will be in when it gets to the other end. So using this for kind of mass communication through internet and stuff, which is something that's been theorized, that you could, have a quantum internet which can teleport messages from one end to the other. Trying to use that is very, very difficult using this technique. So quantum computation, why do we care? Yes, question.
Yes. So so at the end it seems like there's a net loss in particles. If I add one in, what's happening? Is that violating the conservation of energy, or what's going on?
Perhaps. I mean, this is the argument against it, is that, and the reason that many physicists actually doubt that this is kind of, we know it happens, but we don't really know why it happens. We just can observe the effects of it. So you essentially destroy the original and recreate the new one. I can't explain it much more beyond that because I don't know enough theoretical physics to actually be able to understand it better than that. But essentially, that's what happens. We can observe this. We've done experiments with it. So yeah, quantum computing. So why do we care about this stuff? How does it actually affect? How can we use quantum mechanics to compute things? Well, a man by the name of Richard Feynman in 1982, he came up with the idea that we could use these mechanics to actually compute things. And so quantum computing was essentially born. This was a long time ago too. This was 30 odd years ago, 40 years ago. And he theorized that we could do this. But why do we care? What are some problems that quantum computers could solve that are currently intractable? Well, the classical example that's always used is computer security. And take this how you will, it could be a good or a bad thing, but it would essentially completely destroy what we currently use everywhere on the web, everywhere to secure passwords. It would essentially make all the security we currently have completely useless. The way that most current algorithms work is they typically run on an RSA algorithm. RSA 2048 is currently the most advanced algorithm for computer security, and that essentially takes a 2048-bit prime number, and it will multiply several prime numbers together to give you a larger prime number. And the reason it works currently is because actually trying to factor those prime numbers and find its prime factors is basically impossible on a classical computer. A current classical computer to try and solve RSA 2048 would take the age of the universe. It's basically impossible to do. However, using quantum computing, we can use an algorithm known as Shor's algorithm. This mathematician named Peter Shor came up with this algorithm a couple of decades ago, and it would take about 10 seconds to break RSA 2048, which is pretty impressive, and it also is pretty scary because it means that everything we have now will be completely useless. Another typical example that is used is the traveling salesman problem. And this you would think is very simple. You would think that it's very simple to find a solution to this, but it turns out it's actually very complicated. Essentially what the traveling salesman problem is you have a salesman here, and you want to find the optimal route between all the cities. You want to find how many ways he can get between all the cities he has to go to. If you have 14 cities, it's 10 to the 11 routes. So that's quite a lot of possibilities. It takes a classical computer about 100 seconds to solve that, as you can see up here. When you go up to 22 cities, it becomes 10 to the 19 possible options. And that takes about 1,600 years on a classical computer. And when you go up to even more than that, 28 cities, it takes the age of the universe for a classical computer to solve. Quantum computers could manage to do 28 cities in a matter of seconds. So what exactly makes quantum computers so powerful, and how can we use these quantum mechanics to essentially compute things? Well, it's basically an argument of bits versus qubits. A bit, as we all know, is 0 or 1. It's a single transistor in a computer, essentially. It can be in either one or the other state. A qubit, through quantum superposition, can be in many states at the same time while not under measurement. I add this while I'm not under measurement in because if you take a measurement of that particle, it can only be in that state while you're measuring it. So you essentially ruin the calculation. But while not under measurement, while it's not being observed, it can be in many different states at the same time. So I want to take a list, for example. In a classical computer currently, if we want to iterate over a list, we'll have to go through every single possibility one by one. And you could do things like multi-threading, and you could intelligently try to iterate over this list. But ultimately, you're only going to be doing one computation at the same time until you get to the end of the list. A quantum computer can take that list and do calculations on every single element at the same time. And that's essentially what gives quantum computers its power, is that it can do all of these operations very, very, very quickly. So here you have the power of qubits. If you have one qubit, it can be in a state of 0 or 1, or anything in between that. With 2 qubits, it can be in any of those possible states up there, or anything in between that. It's important to note that it can be in anything in between that due to quantum spin. It could be 50% up here, 50% down. It can pretty much be anywhere, which is what makes it very powerful. The computational power of qubits essentially doubles every single time, not doubles, it adds a power of 2 to it every single time you add a new qubit. So if you have 2 to the 300 qubits, you're verging on the power of the modern supercomputers of the world. So essentially, between 300 and 400 qubits, you're already starting to get more powerful than today's modern supercomputers. So yeah, we can utilize quantum spin in quantum computations. It's essentially how we can compute things, because like I've already mentioned, it can either be up or down, or it can be anything in between. Also, while I've already mentioned this, it's important to remember again that you can only compute things while it's not under measurement. So as soon as you take that measurement, you completely mess up the calculation and you'd have to potentially start over. A common misconception of quantum computers is that it's going to universally speed up every operation that we do. And that's just not true. For example, browsing the internet is not going to be any faster on a quantum computer. What is going to be faster are mathematical problems that are currently intractable on regular computers, such as modeling the universe or modeling a climate change problem. A lot of modeling problems and a lot of physics problems currently take hours and hours on supercomputers, and they could take seconds on a quantum computer. Potential problems with a quantum computer. One of the reasons they haven't already become popular, Richard Feynman, he came up with the idea of quantum computation around 40 years ago, so it's been around for a while. But the problem with quantum computers there's essentially three major problems. Firstly, if you have an atom in this room right now, say an electron, it's going to be going absolutely everywhere. We have no way of knowing where that particle is. So the only way to compute things is you have to be able to control that particle. How do you control that particle? You cool its environment down to about absolute zero. You pretty much cool it, you have to get it down as low as it can possibly go, because once you get low enough, there's no longer any heat in that electron, and it no longer just moves around randomly. So you have absolute control over what that particle does. A second problem is that currently the software, as we're going to get into in just a little bit, creating software for these machines is immensely difficult. And until recently, it's become basically impossible to do. We're going to get into it. I don't want to talk too much about that because we're going to go into it in a little bit. But essentially, the software for these systems is very complicated. And that's part of the reason I'm bringing this up, is because as we're all software engineers in this room, most of us are, we're very interested in, how we go forward with software. Where's it going to go in the future? Sorry, the third problem that I forgot to mention is that since the way we control qubits is through magnetic waves, we have it, say, in the spin-up position like this, and we essentially resonate magnetic waves off of it, and through that we can control it. But of course, the only way you can control it with magnetic waves is if there's no other external waves. So as well as having to be below absolute zero, you also have to make sure that there's no other wave interference. So you have to completely block it off from outside worlds. Yes?
When you say wave interference, are you talking specifically magnetic waves or just...
Mostly magnetic waves. I mean, in this room right now, there's just thousands of magnetic waves all over the place. And you essentially need to block off everything from the outside world, because anything can affect a small particle like that. So the software, how do we actually program a system like this? And I know you're going to be very disappointed by this, but essentially we don't know. There's currently a few programming languages out there that are attempting to break the problem of coding one of these systems. But the essential problem is that in a standard classical system, you have, say, an if statement. It relies at its core on being true or false, 0 or 1. And while in a quantum computer, you can still have 0 and 1 states, but the problem is you have everything in between. So how do you model an if statement for something like that can be 50% true and 50% false? It becomes extremely difficult. And this is essentially the problem with the software currently, is that trying to model something over using this quantum superposition and the fact that it can be in multiple states at the same time is extremely difficult. There are a lot of people trying to tackle it, however, as we do have a number of programming languages out there that you can currently look into and currently use. Quantum computational language, also known as QCL, is just one of these languages. Essentially, currently this can work on a classical computer. It can emulate a quantum computer, but it uses a massive amount of RAM. It's just for a few numbers of qubits, and the number of operations you can do are very limited in QCL. You can define functions such as Python, such as in Java and everything like that. You can define functions, which is one of the reasons it's becoming more and more used. This is an example of QCL. You can see here at the top, that's what kind of a quantum computation will look like after you've operated on it. All of those 0.33s, 0.35s, and stuff like that, they're all the states of the quantum bit. So essentially you have, this is 0.35, 35% probably in the down position. And then I believe that's actually all they have there. Another language you can use is called Quipper. And I'm not going to go into too many details on pretty much any of these programming languages, but Quipper is actually written as an extension of a common language known as Haskell. I believe there was a presentation recently on Haskell. Yeah. So this is another one that's probably going to become widely used, is because it's a simple extension to Haskell. I'm honestly not sure how it uses classical computers to emulate quantum bits, but it's there. If you guys want to take a look at it, you can just Google Quipper, or I can help you guys after the presentation. Another one is QML. This one was a research project done by a student. I forget exactly where he did the research, but this was a research student, so it's in very, very early stage. early stages of development. I believe it stands for quantum machine language, but I'm also not 100% sure on that. It wasn't there on the website. This is another one that's derived from Haskell, because Haskell is a very, very strong and powerful language, and it's very, very easy to take Haskell and mathematically model something else after it. So current technology, what currently exists? I'm sure this is going to surprise many of you, but we actually have a lot of technology already created. And most of that technology has been created within the last year or two. So there's been leaps and bounds made in this field throughout the last year or two. Perhaps the biggest leap and bound forward is the D-Wave quantum computer. Now this is actually a quantum computer that is on the market right now. If you want to go out and purchase one, it's going to cost you about $15 million, according to some sources that I looked at. And there's a lot of debate over whether this is actually a true quantum computer. And part of the reason for that is because it's very difficult to test if a quantum computer is actually doing what it's supposed to do, because currently it's in such early stages of development that there's not a lot of mathematical functions to actually test these things. And we do have certain algorithms that you can use, such as Shor's algorithm, etc. Is there a question over here? There are a lot of algorithms you can use on these things, such as Shor's algorithm for prime factorization, but it's still in debate whether this thing is actually a quantum computer or not. Despite that, Google and NASA did buy into it, and they did buy one of these things, and they're now, I believe they're using it to comb the stars, essentially looking for life in the universe. So NASA's definitely using one of these currently. Another thing about D-Wave computers is they're, like many companies, are looking a lot into the software side of things, and they've realized that these things are very difficult to program, and they're very, very difficult to understand. And a common misconception, is that only the machine level of code is going to change, and all of our higher level code, such as Java, C#, Python, all those are going to remain the same, and we'll just be programming, and the machine language is what's going to change. That's a pretty large misconception, because, like I mentioned earlier with the software, this stuff, you can't simply use true-false statements anymore. If you want to utilize the quantum realm, you have to account for the fact that it can be 50% true and 50% false. And this is what makes it very, very difficult. But D-Wave is certainly attempting to rectify this problem right now. Another leap and bound forward is the first quantum logic gate. Now, it might not sound like a big deal, but actually creating a logic gate that operates with quantum principles and can actually calculate things and give you a logical output is very difficult. And perhaps the most interesting thing about this is that it was made in silicon, which is currently used for current computer chips. So it would be very, very easy to simply convert from current computer chips to these quantum computer chips using these gates. This was very, very recent. This was only in October 2015. So a lot of this stuff is actually very, very recent. If you want to know more about how this actually computes things and how the logic gate actually works, feel free to ask. Come talk to me afterwards. Quantum internet. So I mentioned this earlier, but one of the things we can use quantum entanglement for and teleportation, people are theorizing that you can use a quantum internet. And we haven't actually got to the stage where we can send legitimate messages between each other yet. But recently, on November 25th, they managed to not only entangle particles at room temperature, which, as I mentioned earlier, needing sub-zero temperatures, that's a pretty big deal that you can actually do this at room temperature. Not only is that important, but they also managed to teleport a particle 60 miles, which is the longest that anyone successfully managed to do it. Finally, we have a Microsoft quantum hybrid. Now, Microsoft came out with an article recently about how they predict by 2025, 10 years from now, they're going to have a quantum hybrid computer that's going to operate in our homes, and we're going to be able to have in our homes. I know because Moore's law is basically coming to an end and it's basically run its course, many, many technology companies, Google, Microsoft, Apple, they're dumping millions of dollars into trying to create one of these systems. So they definitely predict that it's going to be possible within 10 years' time. I mean, I don't know personally if that's going to be possible or not, considering we aren't too far along with it, but that's what they believe is going to happen. So what is there to take away from this? essentially, quantum computers are very fast. They're very good at doing modeling problems. They're very good at breaking some certain classical problems that are intractable on current computers. And they're definitely going to be here sooner or later. I don't know when. And they're definitely going to need some software overlaid on top of them. So as software engineers, we should certainly be looking and researching into the fact that we're going to have to deal with this state of 50% true, 50% false, and we're going to have to try and program these systems. Currently, like I said, this is in very, very early stages, and I'm not a genius, and I don't exactly know how it's going to advance forward. All I know is that we need to do a lot more research into this because it's gonna come eventually, and it's going to need software engineers to develop software for it. So are there any questions at this point? Yes.
If measuring the qubits is what will potentially mess up the state of it, how do you actually extract information from the calculation?
So yeah, something I kind of didn't really mention is that another potential problem with these systems is that the input-output streams. So currently, you do a problem and it comes out at the other side. When you're doing all these parallel computations, how do you actually get an answer out that makes sense? You could potentially suddenly have like thousands of results on your screen of all the possible answers. But algorithms such as Shor's algorithm actually accounts for this by making it so that the best you can do with Shor's algorithm is you can find the prime factors 50% of the time. So essentially what it does is it uses some clever mathematics and that interference pattern that we saw earlier to cancel out some possible options. And then it'll give you the answer 50% of the time. So it'll basically pick the largest probability of what the answer will be, and it'll give it to the screen. But that's certainly a problem that they need to try and resolve with a lot of the algorithms and mathematics, are that you can't possibly look at these millions of answers, so you have to figure out which answer you want and how you get it out. Good question. Yes?
Does entangling require collocation?
What do you mean by collocation?
Like, if I wanted to entangle two particles, do I have to have them like right here next to each other? Or?
Yes.
Okay.
Yeah. So to entangle particles, you essentially have to bring them really close together, and then you have to set their states to be exactly the same. And that's why it's so difficult at room temperatures, because you have to be able to control the states. So if you can't control the states, then there's no way to entangle the particles.
Gotcha.
Yes.
So you talked a lot about programming languages that are being used on these quantum computers, and you made, at least the graphic you showed a little bit of like programming languages that are used today on top of like software that accounted for the 50% true, 50% false. Do you think that software will generally be continued to be written in those languages that we use today, or do you think it will adapt to write entirely new systems?
I think that current languages will still exist. And I think that we'll probably end up adding extensions or libraries, etc., to those languages to account for this new phenomenon. I don't see current software engineers giving up these C# and Javas and Pythons easily. I don't see them simply abandoning them and trying to learn a new language completely. So I definitely think that we'll use the same languages that we already have in place, but they're definitely going to have to change in some way to account for this new superposition. Any other questions? At the back.
So you talked about how they have to shield the bits from like external magnetic forces and stuff.
Mm-hmm.
Is that why they're like the machines are so big they have to like individually shield each one?
Yeah. So yeah, they basically do have to shield each one. Not each qubit, but the entire chip in it as a whole. So inside a chip, you'll basically embed an atom. I believe they're using in the D-Wave computer. I believe they're using phosphorus atoms. They basically will embed the atom in the chip, and then they'll have to shield the entire chip from outside interference. There's a question over here.
Yeah. So, if you can't create a chain of entanglement, how would you create a quantum internet?
Well, you can't create a chain of entanglement, but you would just simply have two particles that were entangled, and then you would basically try to entangle a third one with them, but instead of entangling, it just sends the data across to the third particle. I'm not 100% sure on the exact physics behind it, but I know that's the basics of how it works, so I don't really want to go too into it because I'm not 100% sure on how the physics of it works. Any other questions? Okay, well, thank you for letting me give this talk. I hope you guys will learn something. I hope it wasn't too confusing. And there's still pizza at the back, I believe.